All right, so we can do ray intersect scene, and that's cool. But that works. I know how to intersect a ray with a sphere. I know how to intersect a ray with a triangle. I don't know how to intersect a ray with an ellipsoid, right? Like, you made ellipsoids in your scenes and these elliptic cylinders and things like that. But I don't know what the calculation is. It's actually a god-awful mess, it turns out, if you want to try to parameterize an ellipsoid and figure out the intersection. There's a much easier way to do this. So here it is. I'm going to show it visually. This is something called ray instancing. So the way that I describe an ellipsoid in a scene is I've gone through some transformation matrix, we'll call it M. So that allowed me to stretch out the sphere into an ellipsoid. So for example, maybe it was the matrix like 2, 0, 0, and we're in homogeneous coordinates, so maybe there was a translation it did as well. We'll make the translation 0. So we could imagine that the matrix is maybe something like this. 0, 0, 1, 0. 0, 0, 0, 1. Okay. So that's a matrix that would stretch this out by a factor of 2. So it turned from a sphere into an ellipsoid. But here's what we can do. So this array it had point P0 and point V. And let's say, we have the origin maybe down here. So the origin of our world is there. So this is the origin. Well, what we can do is take this whole thing and stretch it. Hang on, sorry. Let me just say that Inkscape's not going to do exactly what I want, but it'll get close. Okay. But notice what I can do is I can stretch this whole thing. And actually, I'm kind of stretching it this way as well, right? Because I'm stretching towards the origin. And look, this turns into a circle. Or a sphere. And I know how to intersect a ray with a sphere. So let's look at that again, actually. So the ray was going this way. But if I stretch everything like this, I end up back at a sphere. So that's like doing the inverse of this matrix. So the inverse of this matrix, I'll call it M-inv, would actually be the matrix 0.5, 0, 0, 0, 0, 1, 0. Okay. So this is the matrix that's going to squash everything by a factor of 2. So to get there, everything was stretched by a factor of 2, but to undo that and get back to a sphere, I can squash it instead. So this is a really neat trick. It means that if I have things that are transformed and they look different in my world, I can go back to simpler objects that I actually know how to intersect the ray with and compute them there. So what I have to do actually is, so I started with my P0 and my V. What I have to do is, so step 1 is, we'll call this P0T for transform P0. We have to multiply P0 by the inverse transform. We also have to multiply the direction vector times the direction vector for V. So what I'm saying here is this P0 is going to get compressed by a factor of 2. So it's going to move, in this example, it's going to move a little closer to the origin. V is also going to get compressed by a factor of 2 in X. So notice how the V actually ends up pointing a little more up in this direction compared to how it did. Actually, let me show you them side by side. So we end up here. So see how, whoops, geez, what is it doing? See how the Y component basically stays the same? It's trying to be too smart here and figure out that they're the same thing. Whoops. I'm into all sorts of trouble. Okay, so see how the y component stays the same, but the x component doesn't? So this vector, it's like, what I have to do is intersect with a sphere, and then I get this point of intersection, right? But to do that, my vector points in a different direction, right? And it starts at a different location. Okay, so what I do is I then compute on my new ray. So ray P0t and Vt intersect with a sphere. Okay. And actually, it's whatever the sphere was before the transformation, right? So that sphere will have a particular radius, and it'll have a center, and then a transformation was applied. So it's like what shape you put in to your scene graph. It's those parameters. So intersect with the untransformed sphere, and more generally the shape, right? Because these transformations can apply to triangles as well. Okay, so we go back, we pull this back to a ray that we intersect with the untransformed version of the object. But then we have to go back. Okay, so here's where we get very fancy. I'm going to try to only select... Okay, this is getting a little tough. Let's see, I just want to select these things here. Okay, cool. So now I can go back to world coordinates where this thing is actually transformed, and now I have the true intersection. Okay, so if we call the point in transform space, we'll say this intersects at a point, we'll call it P. So intersects at point P. So if I back up, actually, whoops, let me back up here. Okay, I'm calling this point P. And what I need to do, okay, so that's the intersection. And of course, that's assuming that there is an intersection. This ray might not actually hit it. And in that case, it'd be infinity and we're done. But let's say it actually does hit it. Then what I need to do is take this and transform it. So let me copy this here. And I'm going to move this. Oops, I need to copy that as well. Okay. So I'm going to move this back into world coordinates by applying the transformation. And so you see that now I'll have the point of intersection. Okay, so what I have to do is say, so it intersected at a point P. I'll say that the point I actually want, I'll call it PW for world coordinates. And that's this point that I really want. So now we have to actually go back and apply the original transformation. So I say PW is equal to the matrix M times P0, or times P. Okay. So let's walk through that again. We start with this picture here, where we're sending a ray. So let me clean all this up and run through the steps again. We're sending a ray towards an object which has been transformed to live in our world. I don't know how to intersect with that transformed object, but I do know how to intersect with the object that was specified in the scene graph in its untransformed state. So what I can do is imagine that I undo the transformation. So that brings me back to something like this. And the position is of the ray is being transformed as well, so it's actually moving a little towards the origin as well. Okay. So that's step 1 and step 2. So I'm changing the direction vector, and I'm also changing the point, the endpoint of the ray. by applying the inverse of the transformation. Then I could do my ray intersect sphere because I know how to do that, or ray intersect whatever object it is. So I do the intersection untransformed with the untransformed shape. I get an intersection point P. Okay? But that's not what I want. I want to know what's the intersection point in world coordinates. So I actually have to go back. Once I have the intersection point, I can go back. And here I am. So that's saying take the point of intersection and go back. Okay. So this is called ray instancing. And it's just an amazing trick. Okay. So, and something that's even cooler about this actually is, let's not even say that we have P. Let's actually just say that we have the ray parameter. So let's say that we have, so it intersects at point P with ray parameter T. So P is equal to P0T plus T times Vt. So that's what this is saying. Well, actually we don't even need to do the transformation. It turns out we can equivalently get this point Pw by saying Pw is equal to that same ray parameter but applied to the original ray. So Pw is equal to P0 plus T times V. So this is really cool. You can use the same ray parameter on the actual ray that you computed in the instanced coordinates. So it turns out P0 plus T times V will give you this point, which is the same point as P0T plus T times Vt in the transformed coordinates. So you can use the same ray parameter too. So that'll save you a matrix multiplication, actually. Okay, so this is the way that you should do it down here to be a little faster. Okay, there's just one more thing though that we need to do. When you do the intersection here, you get a normal, right? So it looks like the normal is probably around here. If you remember, there's something a little weird about normals and transformations. So if I take this thing and try to go back, the normal doesn't stay normal, it turns out. So there's another matrix that we need to deal with the normal. So let's say we're in untransformed, the untransformed shape, and we end up getting not just an intersection point P, but we also get a normal. To get the normal in world coordinates, I'll call it NW. There's another matrix we need to multiply that by called the normal matrix. And I haven't derived what this is because I think you probably won't remember the derivation. But the GeoMatrix library can compute this for you. It's actually the inverse of the transpose of the upper 3x3 part of this matrix. Okay, whatever. For those who are actually in linear algebra, I can explain why. But this is what you have to do. So to get the final position, you compute the ray parameter in untransformed space, and then you say, okay, the final position is my actual ray in world coordinates P0 plus T times V. For the normal, you get the normal in untransformed, but then you have to multiply it by this normal matrix. Okay, so that's how you do ray instancing. And that's a 10-point task on the ray tracer to do that. And again, it's just amazingly powerful because I don't have to know how to intersect a ray with an ellipsoid. If I know how to intersect a ray with a sphere, then I can intersect a ray with an ellipsoid just by pretending that I was intersecting with a sphere, but then doing the transformation and going back. Okay, so these are the steps you have to follow. If you follow these steps, it'll be good. You want to end up with the final point of intersection and the final normal. Okay, so that's ray instancing.